On the second problem, uh, it reads, one night at the Tunisian Knights Casino, renowned gambler Jerry Turner, aka the Missouri Master, is having a fantastic night at the craps table. In 2 hours of playing, he racked up $30,000 in winning and is showing no sign of stopping. Crowds are gathering around him to watch his streak, and the Missouri Master is telling anyone within earshot that his good luck is due to the fact that he's using the casino's lucky pair of bruiser dice, so named because one is black and the other is blue. Unbeknownst to Turner, however, a casino statistician has been quietly watching his rolls and marking down the values of each roll, noting the values of the black and blue dice separately. After 60 rolls, the statistician has become convinced that the blue die is loaded. Use a confidence level of 99% to test the claim that the blue die is loaded. So we want to see whether this die here is a loaded die, implying that there's some weight or something in it which is causing it to land on certain values more often than others, which in fact would then be cheating. So on the final exam here, you're going to be given some sort of hypothesis testing situation, and it's very important to figure out what type of hypothesis test you want to use. There's a lot of different ones we've covered in the class, going from single proportions, single means, single standard deviations and variances. We've also tested two proportions, two independent means, two dependent means, two standard deviations or variances. We've done linear correlations, goodness of fit tests, the contingency tables, the tests of independence there, as well as the analysis of variance, the ANOVA. So there's a lot of different hypothesis tests possible to be applied here. The one that we're going to want to use for this problem is a goodness of fit test. We want to see whether these dice rolls here that are observed fit the expected model for what would be expected on a dice rolling situation. So in these goodness of fit tests, they're always right-tailed chi-square tests. We always assume for the null that the distribution is fit. The alternate is saying that the distribution does not fit what is expected, and so if we're able to reject the null in these situations, we're able to then show them that the distribution does not fit. The distribution not fitting in this situation would imply that the die is loaded. And so we can go through and state our null and alternative hypotheses, our null being that the blue die is fair, our alternate being that the blue die is loaded. So next we want to go through and determine the critical value or the critical values on the appropriate distribution. So this is going to be a chi-square test. It's going to be right-tailed because this is a goodness of fit test. We're told to use a 99% confidence level, which implies that our alpha is 0.01. Our degrees of freedom for these problems is equal to k minus 1, where k stands for the number of categories minus 1. In this case here, the number of outcomes that the blue die can land on, we have the values 1 through 6. So we have 6 possible outcomes or 6 possible categories. And so if we do 6 minus 1, we get 5. And so we're using 5 degrees of freedom on the chi-square distribution with an area in the right-hand tail of alpha being 0.01. So what we want to do is use our chi-square table and an area on the right-hand tail of 0.01 with 5 degrees of freedom. We have 15.086 is going to be our critical value. And so I can go through and draw that in. Our critical region has an area of alpha of 0.01, and that critical value on the chi-square distribution, or chi-square sub alpha, is this 15.086. Next we want to get our test statistic, and this test statistic is calculated using this formula where we take the sum of all the observed minus expected values squared divided by the expected values. And so we need to figure out what all of these expected values are. We can use the table up here to help us out, and we can extend the table. We have our observed values here, our O's, but we need to figure out what the E's are, what the expected values are. Now, if you think about it here, if you were rolling a dice 60 times, and it's a six-sided die, you would expect that if it's fair, that every side should be landed on about the same number of times. And so what we can do here is take those 6 sides and divide 60 rolls by those 6 sides, and we see that we should be getting 10 rolls per side. So we should expect there to be an outcome of 10 per each. And so I can go through and fill in the expected frequency for each of the values on the die would be 10. Therefore, if we have 10, 10, 10, 10, 10, and 10, add them together, we get 60 rolls there with a nice uniform distribution. And now we can go through and use this table and compute some of these O minus E squared values. So if I were to take 16 minus 10, that gives me 6, and then 6 squared is 36. I can do 5 minus 10, gives me -5. -5 squared will go through and give me the 25. I can do 9 minus 10, gives me a -1. -1 squared gives me 1, and so on and so forth to go through and complete this column. Next, I can compute the O minus E quantity squareds divided by E. It's nice here that E is 10 for each of these, because I can just divide each of these numbers by 10, which is ultimately just sliding the decimal over one place. And so now to compute the test statistic, I just need to add all of those numbers in the last column together. And so going through and writing it out, we find that our test statistic is 13.6, and seeing where it lands in our distribution, seeing if our test statistic is in the critical region, we see that it is not. So therefore, we fail to reject the null. This evidence here, it was strong, but not strong enough to claim with a 99% confidence level that this die is loaded. Suppose if we were to do instead a confidence level of 97.5%, then our critical value would be this 12.833, which 13.6 does land in that critical values critical region. And so if we were to change the confidence level a little bit, we would have a different result here. We would be rejecting the null and saying that the die is loaded. So depending on the situation, you're going to want to determine what the appropriate confidence level is. In this case here, I think using a 99% confidence level makes sense, because to go through and really accuse somebody of cheating, you want to be very confident that you are correct, because at least you don't want to be wrong. And so to be extra confident that you are correct requires extra strong evidence, and this evidence, while it is strong, is not quite strong enough to reject the null in this situation. So in this case, we failed to reject the null, and we can interpret our result here by going through and stating our alpha. So our alpha of 0.01, equivalent to a 99% confidence level, we see that there is not sufficient evidence to go through and support the claim that the die is loaded. So ultimately here, until stronger evidence is found, we need to assume that this blue die is fair. Lastly, what we can do is go through and estimate the p-value, and what we can do is use our chi-square distribution again to help us out. We know that we have 5 degrees of freedom, and our test statistic was 13.6, and if we scan across here, we see that 13.6 lies between 12.833 and 15.086, which is in between then these areas in the right-hand tail of 0.01 and 0.025. So therefore the p-value has to be somewhere between the 0.01 and 0.025. That area in the right-hand tail beyond the test statistic goes through and represents the p-value. So we can go off and say here that the p-value here is between 0.01 and 0.025. Again, the p-value going through and representing the area here in this right hand tail.